Okay, hi everyone. I hope this video finds you well. Today we are going to talk about the linked lists, and mainly we are talking about singly linked lists. You can start a new project called Sandbox 9 in your Eclipse, and you may use it for this lecture. So the singly linked list, and before we talk about the singly linked list, we would find out why do we need them. So arrays are cool, but what we want is usually we want to store a bunch of data of the same type together. And we can use arrays, but there is a problem with arrays. What are the problems? What are the advantages versus disadvantages? So you may know this, but basically the main disadvantage of arrays is that you have a fixed length. So you cannot grow them in length at runtime. So the array is a collection that you store a bunch of data of the same or similar type inside. So the linked lists are going to be a dynamic collection. When I say dynamic collection, I mean you can add more data at any point of time, at runtime, always you can do that. So the main structure of a linked list is going to be you have a starter point, you have null pointer, and you have always reference to the next node, and you would have data. But the way you would have them, lined up, is the starter node is going to be either just a startup link, so it's going to be empty, and then you start actually from this point, or you may fill the start point. But the main thing is that every node, and we are talking about nodes. Node is an object that consists of two things: the data part and the pointer part. The pointer is pointing to the next node always. The last node is pointing at null. So a node, think about it as a link. A node contains the data, one or more data fields, may be organized as structure, object, or whatever. A pointer that can point to the next node. So here it is. So in general, actually, we say another node because in doubly linked list, you're going to have two pointers. One points to the next and one points to the previous. So the structure of a node mainly would be a data and a pointer. So this is what I was talking about. You can have a list head, and this is a pointer that points to the first node. Each node would have a data part and a reference to another node part. The last node is pointing to null. These are the most important things you should know by now. So let's talk about something called self-referential or recursive data structures. So they basically contain, as a member, a reference variable of the same type as the class itself. For this reason, we call them self-referential or recursive data structures. It's basically this pointer. A node, this node, is containing this part as a pointer that points to another node. So something from inside of that object points to another object of the same type. A pointer inside points to another object. So basically, when we create it, you're gonna see why we are going to call it self-referential or recursive data structures. So the advantages of linked list is that they are dynamic. So allocating the needed memory while the program is running. And the insertion and deletion of nodes are easily implemented in the linked list. And so their linear data structures, such as stacks and queues, are easily executed with linked list. then they can reduce access time and may expand in real time without memory overhead. So you expand them as needed. The disadvantages, however, would be that they have a tendency to use more memory due to pointers requiring extra storage. That pointer is the pointer that points to the other node. Nodes in linked list must be read in order from the beginning, as linked lists are inherently sequential access. So if you're looking at 23 and the 23 is in the fifth element or in the fifth node, you have to go through the first, the second, the third, and the fourth before you get to the fifth and see that the element 23 you're looking for is there. So they are sequential. Nodes are not stored contiguously, greatly increasing the time required to access individual elements within the list. So the storage of nodes is not contiguous. So also some difficulties may arise in linked lists when it comes to reverse traversing. For instance, single linked lists are cumbersome to navigate backwards, and while double linked lists are somewhat easier to read because of the extra pointer we have, the previous pointer, they are somehow wasting more time for the extra pointer, right? So once again, we are going to use an interface. Why do we use interfaces? For many reasons. I'm gonna just show you some of these reasons. One, they allow a standard set of methods to be used across the class hierarchy. So for example, if you want to define the editable interface, you should support cut, copy, and paste operations. The editable interface can then be implemented by any relevant classes and establish a uniform approach. So any class implements that the interface is going to be able to cut, copy, and paste. This is one main reason. The other reasons would be the interface types allow objects to be referenced by the methods they support without considering their location in the class hierarchy. They make maximal use of dynamic binding. For example, if the parameters can be defined in interface or any classes or methods, you can define them as of interface type and using them in your methods. So these methods can invoke the interface method for their argument without having to determine what class actually implementing that method, as long as that class is implementing that method. So interfaces also support selective multiple inheritance, and we talked about it. So since we don't have multiple inheritance in Java, we have selective multiple inheritance, which is basically you can implement more than one interface while you cannot implement extend more than one class. So also the model key behaviors that needed to be supported. By designing interfaces, you would be forced to partition a big chunk of functionality into a set of behaviors. The amount of details in each interface varies, but the very act of thinking through behaviors will provide a more loosely coupled design. And we talked about loose couplings a lot. Finally, because interfaces are declared independently of classes, they are unaffected by changes to specific class that implements that interface or any thing in the class hierarchy. So here is the list interface we are going to use. So we are going to call, for example, LL list of item, and that item could be any type. So it could be integer, student, or anything you want. So this interface, any class that implements that interface is going to provide implementation to those functions, all those functions, right? So move to position, get a value, move to start, move to end, previous, insert, append, prepend, remove, the length or the size, clear, and all these things. So we can have different implementations. So basically, each list can have its own specific implementation and potential advantages. We can easily switch to a different versions if we use the same interface. So that basically provides loose coupling. Let's now talk about the linked list operations. So basically, the references may be addresses or arrays indices, those references. Mostly, those are going to be addresses. Address of this object, the address of this object, and so on. Data structures can be added to or removed from the linked list during execution. As we said, it's dynamic. Linked list is dynamic structure. So if we are going to talk about linked list versus arrays and vectors, linked list can grow and shrink as needed. You can delete on the spot. You can insert on the spot without. So basically, what I mean is it's not of a fixed size. Linked lists can insert a node between other nodes easily. So if we have this node, you want it to be inserted in this place between this node and this node, you can have it. You can do it. So again, just reminding you that a node is contains two main things: data and pointer. Data could be data fields of integer, student, or anything. A pointer is the pointer that points to another node, which is basically a reference to another node, or null if it's at the end, because the last node in your array list is going to point to null. So remember generics. Generics were introduced to Java language to provide tighter type checks at compile time and to support generic programming. And we talked about generic programming before. So we are going to use a generic code. And this is a generic node. Here is a singly linked list that uses generic as it stores anything. It could be storing integers or students, teachers, anything, any object. And we are going to implement LL list. So we provide all implementation to all the methods we have in this interface. And we are going to have inner class. And this is very important. Why do we use inner classes? So we are going to use inner class to create our singly linked list for our stack. And since basically we have this node class, it's going to have the data part and the pointer. This is the pointer. We are going to call it next because in singly linked list, this node is pointing to the next node and that node is pointing to the next and so on. So every point pointing only to the next. It does not have any previous pointers, just the next. So we're calling that next. And since I said that I'm going to show you why it's called self-referential, because it's a node. It's of type node, which is the name of your class. So a class has a data member, or basically a member, that uses the same type. So this is basically this. It's like, remember recursion? A node calling another point. So this is a class defining a variable of that same class type. So we can have more than one constructor. And one would take the data and the next point. One would take the data and would set the next to null. Or one that you don't have data or null yet. So this is what we need an inner class because the node class, this one, is not going to be used anywhere except in the linked list. So why not having that exclusively to the linked list, right? So the private classes, inner classes, we talked about nested classes before and you know that already. So there are other situations where you actually need to write some code that seems like it belongs in its very own class. And this is what we are talking about, right? Or basically up to this point. But the same time, the code that you want to write needs to be intimately tied. It's not just because we said, okay, we are not going to use Node anywhere else, but also that adds some kind of tightness to this class. So those two classes, the inner class and the outer class, are tied, intimately tied. So the question is what to do in this situation. Well, here is where the inner class comes in. So the main three reasons why do we use nested classes is, one, it's a way of logically grouping classes that are only used in one place. Like the node class, we're going to use it in a list, right? It increases encapsulation. We talked about it a lot. It can lead to more readable and maintainable code, because we can say now the linked list is basically structured or created by a lot of nodes. So the single linked list consists of nodes. Now you can read it this way, so it's more readable and maintainable. Anything I will change on the node, it's going to be immediately effective, changing that to every node in that singly linked list. Okay, so with generics, we can create a class generics allowing classes to have members that use template parameters as types. For example, item here could be replaced with anything. As I said, integer, double. You can have the student, teacher, anything, person, anything. So here are the main two things we are going to deal with today. The first one is the data part, and it's going to be of type item, whatever item you are replace it with, like integer, student, and so on. And the pointer part, the next. Next is a pointer of type node, as I said, with the self-referential or recursive implementation. Now, we need to keep track of these things: the size, the current, the head, and the tail. The head is going to point at the very first node. The tail is going to point at the very last node. The current is where we actually now sitting if we're moving between the nodes. And the size is how many nodes do we have in our linked list. So here it is. When you initiate your linked list, you're going to have the current, the tail, the head, all of them equal new node. So basically, every pointer is pointing at an empty node, right? The start link, we are going to call it. And the start link is pointing at null, because now we know if we have this, and the start link is empty thing, as you can see, it's empty node. So that means we do not have any nodes. And this is not actually a data or a node with an actual data. It says just a dummy node that points to or refers to the first node of the class. And since it does not have any data, it's not actually counted as part of our size. This is why we say the size is 0. Now when we start adding more nodes, we are going to move the size by 1, or to add 1 to the size when we add each node. So if a list currently contains 0 nodes, it is an empty list. Or in the case of a start link, it has 1 node, but still the size is 0, because it's not an actual, it's an actual node. What I want to say is that it does not have an actual data. So in this case, the list head points to the dummy first node. So a linked list contains 0 or more nodes. So the head is pointing to the start link. Whenever you add a new node, you should make the last node points to the new node, and the new node points to null. Points to null. Always the last point points to null. This is the most important thing in linked lists. because this is where we are going to have all the traversing. So appending a node, step 1 is that you must create a new link or a new node. You create a new link. If you want to use the constructor where you put the data inside, you can. If you want to later put the data inside, it's up to you. But first, create a new node. And you must always maintain the reference to tail and reference to head. So you'd have it once and you don't change them. The reference to head, if deleting a node, you may delete that. Or in this case of a start link, you don't have to. But the reference to tail is always changing when you insert a new node. So assuming we have 5, 13, 16, 19 in our linked list, we are going to first create a new node, the one we are adding. Then we set the value in the node to the new level, so to the new value, and we set the new link's next pointer to null. So now you can do all these things, the first 2 steps, using the constructor where you have the constructor that takes the data and the pointer. Take the pointer to null and the data to the 21 you have. So that's it. That's it. So the next thing, step 3, is going to be inserting that node at the very last. So remember what we have is this. So the reference is pointing to the last node and the one before last is pointing to the last node. So where are we going to put this new node? We are going to put it in here. So this is pointing to null, which is going to be this. And this link, this pointer is pointing to that new node. That's it. So using the pointer to tail to find the last link, the last node, we set the last link's next pointer to the new node. And then sets the pointer to tail to the new node. So basically, possible implementation of a node when we start is this. This is going to be the start link, right? But then here's how we actually, this is how we actually print nodes if we are going to print. And this is where it comes the use of null. Remember when I said I'm gonna use null for traversing? Here it comes. So the null reference is used to indicate end of list. It should always be tested before using references. Can also test the reference itself. So if I'm printing my linked list, I'm gonna create a node temp because this is a temp node where I point to the current, basically the current node I'm putting at. So I start with head.next because remember head is pointing to the start link. So the first node is gonna be this. So I'm saying head.next while temp is not equal null. Print the data inside, then put temp equal temp.next. So basically that does this. This is my temp. Then I'm saying, okay, print this. Is temp equal to null? No, print 5. Then move temp. How do I move temp? This points, which is temp. Temp.next is this, right? Is this. So temp equal temp.next. Then is temp equal null? No, keep doing that until you get this one. Temp now pointing at this one. Is temp equal null? No. Then you do temp equal temp.next and temp.next is null. Now temp is null. When you go to this one, is temp equal to null? Yes, then you go out of that loop. This is actually how we traverse a linked list. So, linked list methods, as I said, you should have it clear all the elements in the list. Inserting the element, this item. So this is going to inside that insert, we're going to do these steps. We are going to do these steps. 1, 2, 3. So this is exactly how inserting an element. So you create a new node, you put the value of that item to the new node, the pointer to null. Then you insert it at the very last and make the tail points at the new node you just created and inserted to the linked list. Okay, so traversing a linked list. As I said, I just explained this, and here it is in writing. So visit each node in linked list, display the content, validate data, etc. So the basic process is you set a pointer to, here it is, set a pointer to the contents of the first link next to our start node or our start link. Why the pointer is not equal to null, process data, whatever you do it, process data could mean like print the data or whatever you want to do with it. Process data, then go to the next node by setting this. So this part is processing the data. This part is going to the next node. This is how we go to the next node. So traversing a linked list is going to be like exactly like this, and keep these notes in mind because you would need them. So the first thing we do, we have a temp pointer, and this is how we actually create a temp pointer. Node item temp that points to the same pointer, or that points to the same node the start link is pointing at. Then each time throughout the loop, temp is set to the current link's next pointer. So we now process this one, then set the temp to the next pointer. Process this one and set the temp to the next pointer, and so on until we get to null. Finally, the temp is set to null, the while loop condition fails and it drops out of the loop. So the next operation, it's very important operation. So our implementation is using a starter link, right? Recall the current reference that I said we are going to use current variable, so we maintain where we are at right now. We are going to use this one. So the next operation, if the current is pointing at the start link, then the fact that the current is set to the start link works in our advantage. Why? Because we now use the next current.next pointer to of the start link to access the first node, to access this. So if we want to check what is the data inside this link, while the current is pointing to the start link, you do current dot next, which is this link, dot next, dot element is pointing at this one. Next is this link pointing the node, so current dot next is actually this node. Dot element gives you what is actually the node. If I do current dot next, you can do that, but then your current.next is going to be talking about this link. Current.next.element is going to access the element. So now it's 5. We are treating current.next as the current node. Current.next is actually our current node. And so on. So current.next.element, to move, always to move, you put the pointer to the next. So current equal current.next. So that is moved right now. So that was there. Now it's here. So now it's here. If you want to know the next element, so basically current is pointing at this node. The next element is going to be this one, 13. Current.next.element is 13. This will allow us to keep track of 2 pointers and make delete and insert easier. And I'm going to show you how. Same thing, if you do current move the pointer to the next pointer is actually this one, the 16. Because now when I put the pointer in here, I'm actually talking about this node. Same thing in here. The next is 19, the next is 21, and finally the current.next is equal null. So inserting a node into a linked list. So basically, what if we want to maintain a linked list in order? That requires 2 pointers to traverse the link. Thankfully, we have the current. So you need 2 pointers. Reference to locate the node with the data value greater than the node of where we are going to insert the node before, and reference to the tail behind one node to point to the node before the point of our insertion. And you're gonna see that in graphics. So new node is inserted between the nodes pointed by those 2 references. Luckily, we have our current node designed to allow us to track 2 references. So here's an insert example. So let's say we are trying to insert 15 in our list. We want to keep track of the list, and we want our list in ascending order if we want that. But we are going to maintain our list in ascending order. So let's try this out. So here's the list we have, and we are inserting 15. Here's the list we have, and we're inserting 15. So thankfully we have current that points to the start link. So we use the next pointer of the start link, or basically the current, to check the element. So check the current.next.element. What is the value? It's 15. Is it greater than? It's 5. Is it greater than the 15 we have? Not yet. No. It's less than 15, so we continue. We move on. Move on, and then check the next node, the next node's element. It's 13. Is it greater? No, not yet. So it's less than 15, so we continue. Now 13, current is pointing at this node, right? Because we moved it. Now, what is the value inside the next node? It's 16. So now we know that in here we have 16. And in here, we know we have something less than 15, right? Something less than 15. It doesn't matter that much that you know it's 13, as long as what we want for inserting and to keep things in order is to know what's inside this one, the next one. So now your pointer is at this one, and you know that this one is having 16. So now you are for sure have the knowledge you need to insert the 15 in here. Right? So the way we'll do it is this. 1, we create a new node, and we put the value inside the value 15 inside that node. So now, temp references the new node. This is our new node, the one we created. 2, we would set temp.element to 15, setting that value inside. Now set temp.next to current.next. So now this node is actually pointing at the 16th node. Well, not at the 16th node. Basically, the value 6, the node that has or contains the value 16. So this is the second step. Third, you're going to say current.next equal temp. The pointer of that link or that node is now pointing at 15, not the 16. So if we have a linked list right now with 15, 13, 15, 5, 13, 15, and then 16. Isn't that a complete linked list because we don't have any thing breaking it? So you're going this. That is actually a linked list. So now you're done inserting. That's it. 1, 2, 3. That's it for the insertion. That's it. So deleting a node, it's going to be used to remove a node from a linked list and requires again 2 references, one to locate the node to be deleted and one to point to the node before the node to be deleted. And again, thankfully we have current. So deleting 16, we are looking at 16. So assuming that we started from the linked list and kept moving, and we reached out the node before the 16. So we found 16 at current.next.element. Because if you're standing at this point, your current.next is actually this. Dot element gives you this. So now we know where the 16 is. And we are going to remove it. And when we say delete 16, it's not going to delete every 16. The first 16 you would find. So currently we know that it's in this point, in this node. And we have actually a pointer at this, which is this part. This is a pointer that points to this node. Right? And current is actually standing at this point. So what we want to do now is this. We delete this. And this pointer is gonna point at this one. That's it. Or to be more accurate in drawing, this point is pointing at this one. That's it. So what we are going to do, one, we save the element 16 in case you want to return it. If your function delete is returning item. So we save the element 16 and we save the link for the 16, which is going to be this one. So save the link pointer and save the element. 2, we then point current.next to 19, which is basically 16.next. So current.next, this one, this part was pointing at 16 at this node. If we do .next, another .next is going to be pointing at this one. So current.next equal current.next.next. Current.next, here is current. .next is this one. Equal current.next.next. Here is the .next, because this is current.next and .next gives you this one. And actually that's it. If you want, now you deleted the 16 actually. If your function is not void, it actually returns an item, returns 16. That's it. Now the garbage collector is going to take care of this and remove it, delete it. The garbage collector is deleting this link. That's it. That's simple. So save the link, point current.next to current.next.next, and return the value if your function is not void. It returns an item. So destroying a linked list, so you should do something, must remove all the nodes using the delete if you want. Remove all the nodes. You can remove all the nodes. Or basically, you should reverse all the links and put their pointers to null. All the links are pointing to null. To do this, use the reverser to visit each node. For each node, unlink the node from the list. Unlinking the node meaning that I'm pointing that to null. Each point would be pointing null. So if I have, for example, this one, this is pointing to null, and current.next pointing to null, same thing, keep doing that. Then each node is not accessible, and the garbage collector is going to collect them all. This is the easiest thing. In the next lab, we are going to create a simple version of a single linked list. We will not need all the methods discussed in here. We are going to use some. You're going to see that when I give you the lab on Canvas. And we'll build a stack using a single linked list. And you should think carefully about where the top of the stack will be and how the list is gonna grow. Until next lab, see you in the next lecture.